first thing we do always import NumPy as NP. So make sure that you do that and you run the cell. And then we read in our files. So this is the code that we used to read in the files. I'll explain it, I'll explain using the first line. So generate from text. You pass in the name of the file that you want to read in this case, censuscodes.csv. The reason why I was saying that the files need to be in the same folder is that you can just call the file direct. If it was in a different folder, you would have to provide the full path to the file so that the notebook would know where to locate that file as you're reading it in. Next is the delimiter. The delimiter shows at what point you should the different words, the different items in the listings should be separated. In this case, it's comma. Remember, these are commas, comma separated value file. And so we need to let gen from text know that it should separate the values at the comma. If it was a different character, if it was a semicolon, if it was a tab or something like that, then you would specify that here. But in our case, we use the comma. Skip header, let me open the file itself. So you see, our values are separated by commas. So that's why we specify that. Skip header, our table has got heading showing what the different counties, what the different values are, but we don't need that for our analysis. And so we ask, the command is given this argument, skip header is equals to 1. It skips the number of rows from the top that you specify. In our case, we are skipping just 1 row. And then use columns. We don't need the text columns. We also don't need the first column in this specific file. We'll need the first column and the third column. We will not need the second column and the fourth column because you're just going to work with the numeric data. And so use calls tells the command which columns to return to us. If we didn't have this, it would have returned all the columns to us. So we do the same for the other 3 files, for the other 2 files, writing the proper file name, delimiter, skipping the first header, and then the specific columns that we want. Run that command, and now we have our data read in. Then now we look at the different files and start finding out, just examining them to see what is in them. So we want to get the first 10 rows from each array and examine their attributes. So I made a mistake last week. It's actually going 10 because it starts counting from 0. 11 brings us back the first 11 rows. So it's just census codes in brackets colon 10, and running that will bring us back the first 10 rows. So we've read in our data. We now are just examining it. Want to get the first 10 rows from each of the files. So like I'd mentioned initially, last week I'd said census codes colon 11, but it's actually supposed to be 10 because remember Python starts counting from 0. So if we give it 11, when selecting the rows, it actually just does, using this notation, it'll bring the exact number of rows that we want. So if we feed in 10, it'll bring back exactly 10 rows, notwithstanding the fact that Python starts counting from 0. So we use this command and not what I'd given last week. So for census codes, we have our first 10 rows. Census PH, this is the file that has the population, housing, and average housing size. Again, we get the first 10 rows from that. And then AD is the file that has the area of the different sub-counties and the density, population density. Again, that returns to us the first 10 rows from that file. Okay, so we've examined the first few rows. Here in this cell 141, we are examining the shapes and the dimensions of the three different files. So we do each of the file .shape and .ndim. Shape gives us how many rows, how many columns, and the ndim is the number of dimensions. So for census codes, we have 334 rows and 2 columns, and it's dimension 2. Census PH 334 rows, 3 columns, dimension 2. Census AD 334 rows, 2 columns, dimension 2. We see that they all have 334 rows each, which is consistent with the number of sub-counties. But we want to analyze the data, and we don't have to keep doing it for each of the individual files separately. So we just combine them into one file, into one array. For that, we use the hstack method from NumPy. There's the hstack method, the horizontal stack, and there's also the vstack, the vertical stack. In this case, we use the horizontal stack because we are combining different arrays of similar number of columns just to extend it into one array that has the same number of columns and the same number of rows, but more columns. We would use the vstack if we had arrays where we have same number of columns but different number of rows, and then we want to combine so that it's all just one long series rows of columns, but with the same number, of rows, but with the same number of columns. So in this case, we use hstack instead, np.hstack, and we call in the files the arrays that we want to combine. We start with the one that we want on the leftmost, which in this case is census codes. Then we go to the next, census PH, and the final one, census add. And once we run that command and we call the first 10 rows, it shows that we have combined the different arrays. So we have our 7 columns, which we shall check just down in the next command. And then we have now all the rows in place. And to verify that, we run the census shape, which returns the 334 rows and 7 columns, and dimension is 2 as expected. So we've combined the different arrays into one array, called it census, verified that we have the 334 rows and the 7 columns as expected. And I want to...
Excuse me, Eric.
Yes.
The shape is determined by the rows and the columns, right?
Yes.
So what exactly determines the dimension of an array?
The number of elements, so to speak. So in this one we have rows and columns. So that's 2 dimensions.
Oh.
If we were to have rows and columns and then a different block, that would be 3 dimensions. Let me scroll my screen back up to the beginning that we had done before. Let me see. So in cell 8, you have 2 blocks, and then for each block you have a row and a column. So that's 3-dimensional.
Oh.
And then if I go to cell 10, you have an overall 2 blocks. And then for each of those blocks, you have 2 blocks.
Yeah.
And then for the single block, you have a row and a column. So this is 4-dimensional.
Oh,
So it's the number of elements that are in the number of distinct grouping elements that are in the array.
okay.
If I was to do, let me just demonstrate, Control Enter. So for this, if I was to do, add a new cell. So d array dot shape, and then d array dot ndim. Shape. Let me see what error, comma, I need. So for the shape, you see it returns 2, 2, 2, 2 because it is 2 rows, 2 columns, 2 blocks, and 2 overall blocks.
Yeah.
And then dimension is 4 dimensions. So that's what determines the shape and the dimensions.
Okay.
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 So give me a second. So now I want to, so I have this on here as a markdown comment, just so that we can know what the different columns stand for. Column 0 is county code, 1 is sub-county code, 2 is population, 3 is households, 4 is average household size, 5 is area, and 6 is density. Now that we have our overall
Hi,
array,
Eric.
yes,
Eric,
yes.
that is in my notebook. I can't get the. It is this line 143.
The census shape, census
Yeah.
dimension.
Yes, it's not giving me that table. So
Oh no, the table is I created a new. Let me send the code for that. If you look at the raw code, it looks like this.
Okay.
So this is what you use to generate the table markup.
Okay.
I don't know if it's going to translate well in chat, but we can try. Let me just send that and see. So put that in a new cell and make sure it's markup, and then run the cell. It should generate this table for you. Okay, now we can do some aggregations.
Okay, thank you.
Welcome. Census.sum. Now this using the universal array functions that we had discussed at the end of the final class. Let me scroll to that. Yeah, so remember they are the universal array functions where you can get different things. You can get different arithmetic operations done. So you can either call them this way, np.square-root, and then you call the array that you want, or np.exponent, and then the array that you want in there. Or you can just have the array itself, and then like in this case that we have done down here. So the array dot sum, so dot whatever aggregate you want. If you wanted the mean, you could actually, I'll just have the mean as an extra output. You can do census dot mean. Sorry, it's 1ems. So census.sum will return the sum, the totals of all the numbers in the array. Dot mean will return the mean of all the values in the array. However, this does not make sense because basically what this method is doing is getting the total of every single number in the array. But some numbers don't make sense when they're added. For example, the county code and the sub-county codes. But even for the others that do make sense, like population and households, again, it still doesn't make sense because you're adding the population numbers to the households numbers to the average household size numbers and coming out with one number. So this doesn't make sense at all. What we need to do, we need to pass in an extra argument. In this case, axis is equals to 0, and tell it that we just want it to give us the sums of each of the columns. So census.sum axis is equals to 0. When we run that command, now these numbers here are the totals for each of the columns. And just to show you that it makes sense, if you look at the population number, it's 47 million, which makes sense. That is Kenya's population. If you look at the area, it is 574,000, which again makes sense. Thereabouts Kenya's area, total area. So this way, with the axis is equals to 0, we get the sums for the columns themselves. If we were to do, let me add a new cell. If we were to do axis is equals to 1, now this again will not make sense. This is now giving us the sums of the numbers in the rows. So the first row, it sums the numbers in each of these rows and gives us the total down here. But again, that doesn't make sense because you can't add county code to sub-county code to population. Therefore, when doing your aggregation, you need to be careful that you are aggregating them in a way that makes sense and not in a way that gives you meaningless results. So for our case, we are not going to use the axis is equals to 1. We stick to the axis is equals to 0. So delete that. But the totals of the county code and the sub-county code again doesn't make sense. And then we have the average household size and the density. For those ones, getting the totals doesn't make sense. So we can clean this up even more. In this case, we can ask it to give us just the totals of the specific columns that we want. So remember to select columns from indexing. We call our array square brackets. We want it to do the operation on all the rows. And so the first pair is going to be no starting point, no ending point. This selects all the rows. And then comma. To select the specific columns that we want, we pass in a list of those columns. So we want column 2, which is population, column 3, which is households, and column 5, which is area. So we have that selection of the columns. And then the aggregate we want is the sum, so dot sum, axis 0, so it's going to sum on the columns. When we run that command, we get our totals. So again, 47 million makes sense. That's 12.1 million households, makes sense. 574,000 square kilometers makes sense. So now that we have seen what the totals are for the different columns, we can go to looking at what the totals are for each county. So as it is, the table, the array just has an aggregate of just has the values for the different sub-counties, but then it's not aggregated by county. And maybe we want to look at the data aggregated by county. To do that, we need to figure out how to get a specific county and how to get data for that specific county. So we need to remember from the Boolean selection and indexing, we used the comparison operator. So here we say we want census, we want all the rows, but we just want what is in column 0 to be equal to 1, which is the county code for Mombasa. So we'll use Mombasa as an example before we go to the rest of the counties. When we run this command, basically it's going to return an array filled with true and false values. Anytime it comes across a cell, an item in the first column whose value is equals to 1, it will return true. So it returns true for the 1, 2, 3, 4, 5, 6 for the first 6 values, but false for everything else. If we go back to our array, you see the first row, we have a 1 in that first item. The second row, we have a 1. Third row, 1. Fourth 1, fifth 1, and sixth 1. But the seventh has a 2, and on, and it goes alternating until we get to counting number 47. So for the first 6 rows, we'll have true. For everything else, we'll have false. When we use that, to filter out just the rows that we want, so we put in the mask, we put in that comparison, sensors, select all rows, column 0, that is equals to 1. And then we feed that into the sensors array brackets, and that's going to return just the number of rows that has this condition met. In this case, we have just 6 rows returned to us, but the other rows are not in place. Did I run this? Let me run this first. Okay. So we've done our filtering, and we have gotten back just the 6 rows of Mombasa. Now, we are interested just in the population. So the next item that we add is a filter that returns just that specific column, all the rows of that specific column. The first part returns the rows of the county that we want. The second part returns just the specific column that we want. Square brackets, no starting value and no ending value for the rows, since we want to get all the rows returned, comma, 2. 2 is the index position of population. And since that's the column that we want returned, that's what we put in there. When we run that command, we get now just the numbers of the population in the different sub-counties in Mombasa. And again, if you compare this to what is in cell 18, you see that, yes, we have 130,000, 162,000, 287, 249, 147, and 213,000. So it has returned to us just the totals and just the values of population in Mombasa County. Now we can go ahead and add them up to get what the totals are. And for that, we just call .sum to run the operation for us. And for here, you'll notice I have not added axis is equals to 0 because this is doing the aggregation in just one column specifically. And so we don't have to tell NumPy that this is going to happen in that specific axis. So we run the command and we get our totals. 1.19 million as expected. We have our total of the population. Now we need to extend this to the rest of the counties. We need to get the totals in each of the different counties. We'll first of all start off using a while loop. While we need to get a counter which is compared, and in this case, we'll just use I, set it equal to 1, which is county code for Mombasa. Specify an empty list called population. This is what you're going to populate with the totals. Then go into the loop. While I is less than or equal to 47, do the command. We are saying I less than equal to 47 because our last county code is 47. If we were to leave that as I less than 47, it would go run through the loop Then the last time it will become I plus 1 will be 46. Come, run, again go 47. But once it comes to test here, I is less than 47, and so it will not run. So we have to do less than or equal to, so that it runs the final one, 47, increments to 48, comes up here, fails the test, and that operation stops. Alternatively, you could also just do I less than 48. So either of the two, I less than 48 or I less than or equal to 47. Inside, we now append to our empty population list the totals from each county. We have our command here that gets the sum, which we just showed in cell 22. The only difference is that instead of having a number, instead of comparing it to a number, we compare it to I. Remember, I stands for the code, the county code. The first time it's going to run through, I will be 1. It's going to get the totals for all the sub-counties where the code is 1. Once it's done doing that, it's going to add that value to our population list. Then the next line is going to increment I to 2. Come back here, repeat, get the totals for the code whose county is 2, and on until it gets to county 47. When we run that, we get back our list of the totals of the 47 counties. We can do the same with list comprehensions. So remember, from the portion we did on list comprehensions, we talked about how it reduces the number of lines of code you write. In this case, all that we did there is reduced to this one line. We have our population variable, and for that we make an NumPy array, np.array. We pass in to NumPy.array this list comprehension. The list comprehension will return a list, but we want to convert it into an array, and for that we use this np.array. And for list comprehension, we want it to return to us these totals. So the total in each county code I, which will stand for the different county codes. So starting from 1, get the total, then go to 2, get the total. So the total for each county I, for I in range 1 to 48. So it's going to get first value 1, substitute it for I, get the total. Go to the next value 2, substitute for I, get the total. And remember, range, the stop value is 1 more than what you want brought back. So the stop value is 48, and so it's going to terminate at 47. When we run that, we get back our array of the totals in the different counties. You remember Mombasa, we had calculated the total before and it gave us 1.19 million. And we know from the reports, the population in Nairobi is just over 4 million, so 4.3. So this again makes sense. We have our data, but we want to sort them. We want to sort them whether it's ascending order or descending order. Remember, this is the sort method, which we use on our population array. When we call it, it sorts everything in place. And so it's going to do the sorting and change the array so that when we call it, it will return the sorted order. So population.sort, when we run the command, I run this one first. When we run the command, we get back our array with the population total sorted from the least to the most. but we want to look at the top 10, not the bottom 10. And for that, we can use the indexing that we had talked about before, passing in the negative index value to show that we want to reverse the items in the array. We don't have a start value, we don't have a stop value. So we wanted to sort everything in the array, and then we pass in the -1 index, and that returns to us the array with the values sorted from the highest to the lowest. There is a NumPy method called flip UD, flip up down, and it does the same thing. You just call it np.flipud, and then you pass in the array that you want to sort in reverse. In this case, we have population, and running the command gives us the same result as the indexing command we used to reverse the array. For these two, however, the sorting is temporary. It does not change the original array. So we've sorted it up here, but when we call it, the original sorting is still in place. We would have to assign a variable to the sorting command so as to get the sorting fixed in place. So in this case, we can just say top 10 population, np.fluid population. We just want the top 10 rows. I'll change that to 10, not 11. So top 10 population, np.flip up, flip UD, call population, and then just return the first 10 rows. When we run that command and call top 10, it's just going to return those top 10 rows in population. When we check the type of population array, you see that it is indeed an ND array, a NumPy array. 47, the shape is 47,0, meaning that it's a one-dimensional array. Again, verified by the population.ndim, it's just one dimension. You have just the one list, one column of values, that's it. You don't have any other columns. And 47, again, verifies to us that it returned what we expected. There are 47 counties, and we expect we expect to have 47 values.
Eric, we can use flip down instead of sort.
So flip up down. Just go back up here. Sort just sorts the array for us.
Yeah.
But flip up down, we are using it to reverse the order of the array. Flip up down is similar to what is in cell 27, population, and then you're passing in the negative index at the end. So flip up down does the same thing as what is in cell 27. It doesn't sort, it just reverses the order of the array.
Okay, so in cell 27, it arranges them in a descending order, right?
Yes.
And in cell 30, it does the same thing.
It does the same thing.
So now if we use flip down instead of flip up, it will give the same result.
If you use
flip down.
This is flip up
flip
down.
Up down. Yes. Oh.
So it's flip up down, flip UD.
Okay.
Yeah, flip up down. There's also flip left right, which does the same thing, but then now does from left right instead of up to down. But in our case, we just want up down, so we use the flip up down, flip UD.
Okay.
Yeah. Okay. So we get our top 10 array population. And when we check it, the type is an NumPy array. Population shape is 47. So consistent with the 47 counties, and the dimension is just 1, since we just got values from the 1 column. Let's try a different metric. This time around, we want to calculate the average household size for each per county. Right now we have the average household size in distributed over all the sub-counties, but we want to aggregate them per county. The command is going to be similar to what we had before. We will just use the list comprehension, and we define our variable average household size. For that, we are going to assign the array we shall create using the np.array method. And the list comprehension, basically it's going to be, we have our command which looks at each county based on the index I. It starts at county 1, gets the mean, goes to county 2, gets the mean. And here we have 5 as the column, because 5 is the column that has the average household sizes. We use .mean. We are not using sum, we are aggregating the mean. So we use .mean for the command. And when we run that, we get our average household size. Let me share that code. When we run that, we get our average household size. We can manually verify that it has indeed returned what we expect. Let's use numbers from Nairobi. So we assign a new variable AHS Nairobi. We just want to get the values from Nairobi, the average household size values from Nairobi. So we do our comparison. Census, we want whatever is in column 0, which is the county index, to be equal to 47. And for those rows whose county index is 47, we want them to return just the average household size column. All the rows, so no starting value and no ending value, comma, 5 being the index position for average household size. When we run that command, we get back our values of the average household sizes in Nairobi. Then we can get the sum of the average household sizes in Nairobi, which is 703.7. We just use the .sum command. And again, remember, because here we are doing the sum over just one column, we don't need to put in axis is equals to 0. Now that we have the sum, we divide it by the number of sub-counties in Nairobi. In this case, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But you don't have to manually count. Remember, we have the len command, which gives the number of items in a data structure. In this case, the number of items in this specific array, AHS Nairobi. If I was to do, let me add an additional cell. Len AHS Nairobi. Oh, I have not run this command. I need to run that command. And then that command. So you see, it returns to us 11, just as we verified manually by counting. We then calculate the mean, the sum divided by the number of items. That gives us back 63.972. And if we look at the array up here, you see that the mean brought back is 63.972, which shows that our computation to calculate the average household sizes was indeed proper. You can also test the two different values for equality. So AHS Nairobi is the value that we have just calculated, and we want to test that against the average household size of the item from Nairobi. You remember, to get the last item in an array, you just pass in the -1 index, and it's going to do, in this case, we know that the last item is position 47. So if we run, let me see, oh, sorry. Yeah, but again, Python starts counting from 0. Always remember that, otherwise it will trip you up like it just tripped me up. So we know the last item is index position 46. So if we pass that, then it returns true. But since, in order not to get tripped up like I just did, if you just want the last item specifically, you just pass in the -1 index, which is going to return the last item. And you've seen that the value in that last item is equal to the value that we have just calculated. Then one more illustration. So assuming we did not have the average household size column, but we needed to generate it from the data that we have with us. Let's just do it for Mombasa. And again, to do it for all the counties, whatever you do for one, you'll just put that into a list comprehension and it automatically generate for you. But for our purposes, we'll just do for Mombasa. We get the rows we want from Mombasa. Remember, we do that by passing in this mask, where we want it to look at the first column and return only the rows where the first column value is 1. So we run that, we get our array with the rows for Mombasa. Now we can calculate what the average household size is. And that is basically just population divided by the number of households. We specify, we declare a variable average household size. And for that, we want to assign to it the calculation resulting on the right-hand side, which is just population divided by number of households. We get our column of population, we get the values of our population. So we pass in, we tell it to just bring back the rows for Mombasa using the code that we have up in cell 43. But for that, we want it to return just the population column. So all the rows in the population column, which is column 2. We divide that by all the rows in the households column, which is column 3. And then we want it to round the answer to 1 decimal place. So we use the np.round method. We call in the array that we want it to operate on, and we specify that we want just 1 decimal place. So when we run that command, we get back our array of the 6 values for each of the 6 sub-counties in Mombasa, the average household size. We can call the average household size column from the table. Again, we want just the rows from Mombasa. And for those, we want all the rows in the 4th column, which is the average household size column. And when we call that, you see that the values are indeed matching what we got from our calculation. So 2.8, 3, 3.3, 3.1, 3.8, and 3.1. That's how you will create a new column if you did not have that column in place, but you needed a new one generated for whatever analysis you need to do. Then the very last thing that I'll touch on for NumPy is a method called random.choice. You have a list of data and you want to do some analysis on it, but you want to get just a random selection from that data. You want to sample different items in that data, run a test on that before you can do it now for the overall big set of data. In our case, we only have 334 rows, which is not that huge of a set of data compared to records where you can have millions of rows. And so it will not be computationally intensive to do whatever tests we need to do, but assuming that is the case for us, and assuming you just want to do computation on a smaller subset of numbers. So you use the np.random.choice method. Then you pass in the column that you want. In this case, we want the population column. And we want all the rows from the population column. We want it to do the selection from all the rows in the population column. And you want it to return just 20 values. This command will go through census population, the column, and return 20 values at random from the 334 rows that are in that column. So if we run that, we get the different random values. And every time I run it, I get different random values. So that's what I had for NumPy.